I think I was confused on the A imply B, but now I feel like a little better.
Uh-huh.
I practice now.
Sure.
If you show me one more time, that will be
I'll
yeah.
be glad to.
Yeah, I practiced already and I did my homework.
Great.
Mm-hmm.
All right, so the conditional. A implies B. And it's got a truth table. You can help me fill out the truth table so that we can just review the rule for when it's true and when it's false. Okay? So you want to help in row one?
Okay. So there is true, true. The row one will be true.
All right. How about row two?
And then true, false, false,
Yeah, true implies false is false. That's when it fails.
false. And then the false, true, true, right?
Yeah, false implies true is true by false hypothesis.
And then false, like false and false will be true.
By false hypothesis.
That's false. Yeah, because I practice now, like I I just did my homework 2.3, and then there was play, and then I practiced, I searched the video, and then I searched everything, and then now I got this better.
That's good.
Yeah, I was so confused. That's why now I feel better.
Good. So in the material um two, the measure, I guess it's measure two material actually. The measure two material on the website. There's a document now. It's called what is it called? Let me take a look online because I just posted it. There's a new worksheet to practice. And I'll share my screen with you. So under measure two material, there's a review worksheet. And so it's kind of nice because the first problem involves two implications. And you can practice deciding if these two statements are logically equivalent. They're both implications. And the solutions are posted. Okay.
Okay.
And then there's practice on the converse, the contrapositive, the inverse, and the negation for two different statements.
Okay.
So you can use De Morgan's laws and what you know about the converse and the inverse and the
So there is if the sun is a star, then the earth is a planet, or the earth is a moon.
That's right. So
So
this
the if the P will be P imply
Q,
Q or R
yeah,
and or R.
yeah.
So we have to write that like that also.
I think it would help you, yeah.
Okay.
Okay. And then there's another problem where it's P implies Q
U N.
and R. Uh-huh. So you get to practice.
Okay.
And number four is a problem that's an if Ooh, there's a typo here. This should say, if it rains and it pours and, oh no, it's correct. And if it pours and it rains. So the point is this statement is P implies Q and Q implies P. That's what this is. This is actually the biconditional statement.
Oh, yes, yes. I got it.
So some of these, maybe many of them, are logically equivalent to if P then Q and if Q then P.
So for the logical equivalent, the column must be like identical, right? Like,
Yeah, but you can actually do number 4 without making a truth table. Let me help you with the first one.
okay.
Okay, so the name of this is a review worksheet for sections 2.1 to 2.3. So if we look at number 4, it says, if it rains, then it pours, and if it pours, then it rains. So you could make a key where P is it rains and Q is it pours, right? And you can see that this original statement, the one that's given, if we write it using P's and Q's and symbols, if it rains, then it pours. So how would we write that?
Oh, sorry. P imply Q.
Uh-huh. And then there's an and, so there's the and symbol.
And if it pours means Q. Poor Q. Yeah. So Q imply P.
Great. So the original is actually the biconditional. Okay. So we look at each statement that's given and we try to discover if it is if it is both of these, if it is P, if and only if Q. So let's look at number A. A says, if it doesn't rain, then it doesn't pour. And if it rains, then it pours. So let's see if we can parse it out using our key, P and Q, okay?
Okay.
All right, so let's go ahead and write it formally, and let's see if we can figure out if it's going to turn out to be P implies Q and Q implies P.
Okay. So if it does not, if the it's not P, then imply not Q,
Good.
and P imply Q.
Okay, so now here we can just use the fact that this is called the inverse of P implies Q, but it's logically equivalent to its contraposition. So how could we rewrite this in as an if-then that's logically equivalent?
For the
Do you remember how we would write the contrapositive of this? We switch everything. We switch the P and the Q position and we negate both of the components.
so not Q,
It'd be not
Q,
Q.
and imply not P.
Not P.
Oh, not P. Okay.
Yeah, because this is logically equivalent to its contrapositive. This is these two are contrapositives of each other.
Okay.
And we have P implies Q. So now we can simplify this. What's not Q?
Not, not, no, I write it down, but
All right, I can help you. Let's say we have A and we have not A and we have not A. Okay, let's say we're trying to understand, what not A is. Well, A could be true or false. What are the truth values for not A?
false and true.
And now we're going to negate that. So it flips the bits back.
So false, false, true,
Yep.
and then it's gonna be true and false, right?
So we're going to flip the true back to a false. So you see how A is logically equivalent to not
Yes.
A?
Okay,
So not Q is the same thing as Q. If you have two nots, they cancel each other out.
okay.
And then what does not P become?
Not P become P.
Good. So not P implies not Q is logically equivalent to Q implies P. This is called the inverse. This is the converse. Remember, they are logically equivalent to one another
Okay,
if the original is P implies Q. So we have Q implies P, and we still have P implies Q. So we do have both of them with an and. So it is logic. It is the same expression. We're just getting at that answer by using the logical equivalence of different ways to say if P then Q and
yeah.
if Q then P. So this is logically equivalent to the original because we have both this and that. I'm gonna share my screen one more time.
Okay.
And I'm going to just remind you of another resource that's really helpful in the good stuff folder, the if P then Q document, which tells us all these different ways to write if P then Q, different ways to write if P then Q. You can write if P then Q or P implies Q. You can write P arrow Q. So these first three we understand. They all mean the same thing. But there are other ways to say if P then Q. One way is to say Q if P. Another way to say if P then Q is to say P only if Q. Another way to say,
What I meant, P only if Q.
yeah, the intuition behind that is this. If P then Q means if P is true, then Q must follow and also be true, okay? Well, P only if Q says P can only be true if Q follows, if Q is also true.
Okay.
That's why P only if Q means the same thing as if P then Q.
Okay. And then
So here's a couple more ways to say if P then Q. You can say P is sufficient for Q. P being true is sufficient to force Q to be true.
okay.
Q is necessary for P, right? Q must necessarily be true for P to be true.
Okay.
Q when P is another way to say it.
That means Q is true when P is true.
Yeah, Q is true when means if.
Yeah. Imply. I mean the then.
Yeah, but it means, Q when P means if P then Q.
Okay.
And here's the contrapositive. See, we've been using that in this exercise. That if P then Q means if not Q, then not P. That is the contrapositive. See, because up here you can see the original conditional has these sisters, right? Well, the one it's logically equivalent to is the contrapositive. If P then Q means the same thing as if not Q then not P. And the converse, if Q then P, means the same thing as if not P then not Q, because converse and inverse are contrapositions of one another. You just have to switch the P's and Q's to see it.
Okay, the converse on the Q and P, the Swiss the equivalence.
Yeah.
Mhm.
And there is one other way to say if P then Q, and it's actually an or statement.
Not P or Q.
Yeah. And the intuition behind this is either P is true or it's not. If P is true, then we know we get Q because P implies Q. If P is not true, then we don't have P at all. So either we don't have P, which is not P, or we do have P, in which case we get Q. So either not P is true or Q is true. This is you can check it with the truth table.
Okay.
Not P or Q has the same truth table column as P implies Q. You can check it.
Yes.
And then this is just a verification that the negation looks like P happened and Q did not follow. This is the negation, P and not Q. We talked about that in class, but you can verify this. You can make a truth table and build up to a column for the negation of if P then Q. So, you would take this column for if P then Q, and you would just flip everything because you're going to take the negation of that quantity. And then you can build up and make the column for P and not Q. And you'll see that P and not Q looks exactly the same as the negation of P implies Q. So it's good to kind of convince yourself all of this stuff is really right. And this exercise, this worksheet was designed to help you practice um, these ideas, and the answers are all there to look at. Because see, these are all a whole bunch of ways to say different implications. And you can refer to that if P then Q document to help you figure out if you actually get both P implies Q and Q implies P as you check each one of these to see if it means the same thing as P implies Q and Q implies P.
Okay.
And it's definitely possible that many of these will be logically equivalent, but some may not. So you can check those. So I encourage you to work through those as practice problems. This is the review worksheet in the Measure 2 Materials folder. Hey, Nura.
Mhm. So, okay.
Evening.
So we're just looking at this, we're just looking in the Measure 2 material folder, and we're just looking at a review worksheet that has some nice practice problems to go over to help reinforce everything from sections 2.1 to 2.3. And the solutions are up. So we just talked about a few of those. Do you have any specific questions, Nura?
I went over the previous material in the special homeworks. I was hoping to go over my key with you.
Okay, for what?
It was, I have it up. On the sister conditionals and the biconditional, the three examples.
Was it a worksheet or
Yes,
which
it
one?
um
Conditionals and biconditional?
yes, it was worksheet on conditionals and biconditionals. It was due on the 11th.
Yeah, okay. All right.
Yeah. Uh,
So you made a key for example 1 to try to figure out if A, B, and C were logically equivalent to example one? Okay.
Yes, I did all three, and I already have what I came up with. So I was hoping I could get you, I could, just share it with you and get some feedback.
All right. So what's your key for example one?
I used P for if the train comes every hour,
Okay.
and
I would just FYI, we
uh-huh.
usually don't put the if in the statement P because it's if P then Q. So P would just be the train comes every hour. Does that make sense?
Yes.
Okay, good.
And then for Q, I said I will get to work on time.
Perfect. So this first one is if P then Q. Okay. So what did you come up with the A, B, and C there?
For A, I got that it was the contrapositive.
That's right, because it's if not Q, then not P. That's right. That's a contrapositive.
For B, I got that it was the inverse.
Correct. If
And
not P, then not Q. Good.
for C, I got it was the converse.
Correct. So are any of those logically equivalent to the original if P then Q?
Only the contrapositive.
The
Only
fir-
A.
that's correct.
Okay.
Great.
Okay, for the second example,
Uh-huh.
it starts out if Bob isn't a math major, then he won't take math 267. That's the So I put it down as the contrapositive because that's its form.
That's
I don't
fine. You can say, so what did you, in your key, what did Bob isn't a math major? How did you represent that?
I put not P equals Bob is a math major. Oh,
Is or isn't?
it should be isn't.
Okay, so this is your not P.
Yes.
Okay, and then what did you do with he won't take math 267?
I made that not Q.
Okay, so we have if not P, then not Q. Okay, I can follow with that.
So then for A, I put P implies Q.
Okay.
I took the negations away. I didn't write it out fully that it's not P, but I probably should have done that.
No, you don't have to. It boils down to P implies Q.
Okay, so I put P implies Q, and I said that was the inverse. No, the contrapositive. Yeah, that's what I put.
Uh,
No, it's the
no,
converse. I'm sorry.
it's the inverse.
Oh,
Because listen, here you have Bob isn't a math major. But when you negate that it's not true that he isn't, then he is a math major. So this Bob is a math major is the negation of Bob isn't a math major. So this is
uh,
so this statement right here is the inverse of this statement.
okay. So we always compare whatever the original statement is the statement we are comparing everything with.
Yes. Because, even if it's got some knots in it, it still is an implication. So it still does have a converse and inverse and a contrapositive, whether it's got knots in it or not.
Um, okay. So the letter C, I made that the contrapositive.
It is the contrapositive of example two original. It is.
Okay.
So
E
that's the one that would be logically equivalent to the original in example two. That's right.
okay.
I mean,
Even
basically, we're changing the positions of the two statements. The Bob and math major, is now over here. And the take math 267 or don't take it is now the hypothesis. And they've both been negated in this statement C. So the statement C is the contrapositive of this original.
I see.
Like every if then has a converse, an inverse, and a contrapositive. Even an if then that has some knots in its construction.
I see.
Do you want me to write something down on the paper for you?
No, I'm following along. It's just I was a little confused about the contrapositive not having any visible knots, but then I remembered that we negated the knots.
And
So,
that disappears them.
yeah.
Exactly. Very good.
Okay, so for the third example, that's a biconditional.
It sure is.
Okay. So I got a little confused on the conjunction signs, but for the first for letter A, okay, my key is
Yeah, I'm
P
going to write this one down. This is example 3 in the worksheet, and I'll put the title here in a minute. All right, so what's your key?
for a polygon is a triangle. I use the letter P.
Okay, P is a polygon is a triangle. Got it. I like it.
Q, I said it has three sides.
Okay, a polygon has 3 sides, or you could say it. It's okay. We know what you're talking about. All right, so that's a very good key. So what we have is, our original, like you said, it is P if and only if Q,
So it's a polygon is a triangle if and only if it has three sides. Okay, I see.
right? So we have basically P implies Q, and we also have Q implies P, because that's the meaning of the biconditional. It means we've got a conditional going both ways, right?
Okay.
So
So
I'm
when we see a biconditional, we can
uh-huh.
always assume that we can write it two ways.
Yeah, oh yes. And in fact, this is the way that's going to help you. Writing it as a conjunction of an implication and its converse is the way that's going to really help you analyze whether it's logically equivalent to some given statement. For example, statement A is, if a polygon is a triangle, then it has 3 sides, and I'm just going to go ahead and just, space it out. Um, I don't really need a capital. If the polygon has 3 sides, then it is a triangle. So what we're going to do is use your key and try to figure out if this statement A turns out to have both of these with an and between it. Of course, there is an and there.
Oh.
See, because your key is really going to help you with this. So let's go ahead and try to write statement A using your key. In other words, let's write statement A formally.
That would be P arrow Q.
Yeah, if the polygon is a triangle, then it has 3 sides. So that's P arrow Q. Good. And there's our and, right? Because these all have an and in there. Okay. And then
We have Q arrow P.
right. So we do have both. P implies Q and its converse. And that's what we're trying to figure out if we have. Because the question is, uh, you know, circle all statements that are logically equivalent to the original statement. Well, the original statement was P if and only if Q, Maybe I should write it up here. The original is, a polygon is a triangle if and only if it has 3 sides. So, we started with that if and only if, P if and only if Q. Right, and you made that nice key. So A is definitely the biconditional that's the same as the given one. It's just written differently. So you can circle that one. What about B?
Okay. For B, I got a little confused. I said
Okay, I'm
not,
gonna write it down. If
okay.
the polygon isn't a triangle, then it doesn't have three sides. And what was the other statement? If the polygon doesn't have three sides, then it isn't a triangle.
Um, yes, yes. And if the polygon doesn't have three sides, then it isn't a triangle, yes.
Okay, great. Well, you have a good key to depend on here. So let's write it formally and see if we can figure it out.
I used not P, so I still have P, so not P,
Yeah, we're going
arrow.
to use the same key throughout the whole game. Okay,
Okay.
so not P. The polygon isn't a triangle, would be not P. Okay, arrow.
Not Q,
Yep,
and then it's and again. So
yep.
and, okay, and then not Q,
Uh-huh.
arrow, arrow, not P.
Exactly. Excuse me. I'm so sorry. Who is that? Uh, I, I'm so sorry. Hang on just a minute, please.
Okay.
Okay, sorry about that. Great. All right, that's exactly what the statement says as per your key. Okay, so now we want to kind of boil this down to an equivalent form to see if it turns out to be this. No,
Okay.
turns out to be the original, excuse me.
When I was doing it, I got confused because not P, arrow, not Q is the inverse of P implies Q.
But it is logically equivalent to its own contrapositive. Like there is
Oh,
a logically equivalent way to say this.
oh,
Because remember the procedure, you know, to get from P implies Q to its contrapositive, you switch the P and Q and you negate them both. Well, to get to the contrapositive of this expression, you switch these two components and you negate them both. But when you
oh,
negate them, it flips them back to just regular Q and regular P.
oh. So, okay, just so can you repeat that?
Uh-huh. This is an implication, and yes, it is the inverse of if P then Q. It is. But it has its own contrapositive. It has its own three sisters, and it's logically equivalent to one of its three sisters. One of its three sisters is its contrapositive.
Okay.
Like even though we call this is the inverse of P implies Q, but it has another form, a logically equivalent form, where we take the two components and we switch their positions, that we flip where they are, and we negate both components. So this is not Q implies not P. It is logically equivalent to its contrapositive. This is the contrapositive of that. And of course, this is the contrapositive of P implies Q. But you can also just, go through it. This is not P implies not Q. See, this becomes P implies Q. We know that because this is the contrapositive of P implies Q. But this has its own contrapositive, which we get by this procedure, and its contrapositive is the converse of the original.
So we negate both sides of that statement?
These are called components. So to
Component.
find the logically equivalent sister to any, it doesn't matter what it is, any implication, no matter how complicated the components A and B are, to find the contraposition, which is logically equivalent, you switch the positions and negate them both. You switch the component positions, right? And you negate them both. So if you're negating something that's not Q, you're getting not Q, and that just boils down to Q. In other words, these two are logically equivalent to one another in the same spirit that P implies Q is logically equivalent to its contrapositive. These are contrapositives of one another, just the way these are contrapositives of one another. But we call this the inverse of P implies Q. This is the converse of P implies Q. This is the contrapositive of P implies Q. But each one of these four has its own four sisters.
And that's represented in the sentence. If the polygon isn't a triangle, then it doesn't have three sides. And if the polygon doesn't have three sides, then it isn't a triangle. It means the same thing?
Yeah, it means the same thing as the polygon is a triangle if and only if it has three sides. Because we're getting both, we're getting both P implies Q according to your key, and we're getting Q implies P as per your key. And that's what the original was. It was the biconditional that had both P implies Q and Q implies P.
Oh.
I know. It's kind of deep, isn't it? It's kind of confusing. And there's another one, isn't there? It's another statement. C. If the
I just saw
polygon is a triangle, then it has three sides. And if the polygon doesn't have three sides, then it isn't a triangle. I'm just going to put the symbol triangle there because I'm running out of room. But here's your nice key. Here's your key that you made up. And we're trying to check the logical equivalence to that original. So using your key, how would we write C formally?
P arrow Q.
If polygon's a triangle, yep, P arrow Q, good.
And we not Q arrow not P.
Exactly. So now we want to, check and see if this is giving us both P implies Q and the converse. Well, let's see what this is logically equivalent to. P implies Q will keep, right? Because it's helping us get there, That's half of it. But what is not Q implies not P logically equivalent to?
It's logically equivalent to P implies Q.
That's exactly right. So it turns out we've got two copies of P implies Q. And if you have, by the way, if you have A and A, that's the same thing as just having A. You can check that with the truth table. You can make A, and then you can say A and A. A is true or false.
So I have one question.
Uh-huh.
So how to know if there is how they are logically equivalent, if there is only different something like
You should review the if P then Q document. And the main thing to realize is that the contrapositive, not Q implies not P, is logically equivalent to P implies Q.
So we have to remember that, or it's
yeah, that's the one you need to remember.
okay.
And then it just makes sense. If you have the same statement twice, anded together, if you have A anded with A, that's the same thing as having A. Look at their truth columns. They're identical, right? True anded with true is true. False anded with false would still be false. So having something twice with an and between it you don't need it twice. Once is enough because it's the same thing. You're saying the same thing. I've got P implies Q, and okay, I've got it again, but I don't need it again. That's redundant. We have P implies Q. Does that make sense?
Yes. Okay.
And it's the same way with or. A ORed with A, that's just A. You can check it, A ORed with A. True ORed with true. Oh, yeah, that's true. False ORed with false. That's still false. You see, there's no value added for having multiple copies of the same statement, A, right? With an and or an or between the copies. I mean, it's not wrong. It just doesn't help you build anything new. You did a nice job with this, Nura.
Thank you, Professor. I just wanted to make an observation for the using the same value on both sides of I guess that's the argument. I don't know.
You mean
But
this?
yes, your truth table that you just made, if
Ah,
you said A implies A, then you would
ooh.
have different values. They would both be
Oh, that's another. Yeah, let's look at A implies A. I like it. So in row one, we would have true implies true. What would that be?
true,
And in row two, we would have false implies false.
which is true by false hypothesis.
That's right. And this is the point. Think about it. What A implies A means. It says if you have A, then you better have A. I mean, that's what A implies A means. It means if A is true, then A has to be true.
Ah.
That's
So for the false values, you would say you don't have A, so you don't have A, which is true.
right. Because false implies, yeah, it's true by false hypothesis.
Ah. But
It's
they're not
interesting.
but they're not logically equivalent.
A is not logically equivalent to A implies A. No, it is not. It is logically equivalent to A and A. A is logically equivalent to A and A. A is logically equivalent to A or A. But A implies A is actually a tautology. It's always true, whereas A is not always true. It's true sometimes, and other times it might be false.
Ah.
So, yeah, one of the ways to investigate that was a really good question, by the way, Nura. That was a very insightful question, is to just make truth tables and investigate, hey, what happens, when the hypothesis and the conclusion happen to be the same statement form? And in fact, I'm going to share my screen one more time. I want to go back to this other little worksheet, this review worksheet. And again, the solutions are up, but I like that you really worked hard to get the answers. On this particular practice, problem number one, where you're going to draw a truth table to see if these two statement forms, one and two, are logically equivalent. Use the information in your truth table to discover if one and two are logically equivalent. Take a peek at what happens in that truth table. When you'll answer the question, I'm sure. You'll make a truth table and work up to a column. You'll need 8 rows. You'll work up to a column for each of these two eventually, and you will compare them and you'll make a decision if they're logically equivalent or not. But then in the answer key, when you check it, I have actually added another kind of investigation question for you to then even look one more time at that truth table and see something interesting that you'll observe happens in that truth table if you did it correctly. So it's all about just, give it a try, see what happens.
Okay.
I'm telling you, the best resources that we have right now are the if P then Q document in the good stuff folder. Like that's a ready reference. And then just remember a few things. P implies Q is logically equivalent to not Q implies not P. And in general, P implies Q is not logically equivalent to its converse.
Oh,
Like if you just remember a few things, remember this and remember that. But then you have to remember one more thing. When we write down the rules, like this rule says the original is logically equivalent to its contraposition, and the original is not logically equivalent to its converse, we pick a single letter to represent the hypothesis P and the conclusion Q to write the rule. However, when we apply the rule, the hypothesis we're applying it to could be significantly more complicated than just a plain old P. In other words, and there's some practice on that, but here's an example. Write the converse and contrapositive of, here we go. P implies Q or not P implies Q implies, okay, so this is like our big P, you can call it curly A. P or not Q.
well,
See what I mean? Like we used a P and a Q in the rule because we have to use something to write the rule. Okay. Or you could, substitute an A and a B. But when we try to apply the rule, we may be recycling the variables P and Q, and we have to understand that in some sense, this is like the big P, it's the big hypothesis.
so when we're manipulating those values,
Uh-huh.
we're we're using the two full sets of brackets, I
Yeah,
guess.
yeah. Well, yes, I did go ahead and put the brackets, although and does take precedence over the arrow. I didn't really need these brackets here, but I put it there to emphasize that this whole thing is the big hypothesis, and this whole thing is the conclusion.
Oh,
I tend to overkill with parentheses. But the point is, all right, let's say we want to write the converse. The converse is easy, right? Because the converse is going to be curly B. And see, notice I've changed the letters now because I'm using a bunch of P's and Q's here. So even though we learned the rule with P's and Q's, we may be presented with a problem that uses P's and Q's inside an implication where we might decide to rename the hypothesis with a different letter so that we can kind of just get the big picture. This whole thing is the hypothesis now. I'm calling it A. This whole thing is the conclusion. I'm calling it B. So when we get ready to write the converse, at least I remember, okay, the converse of big A implies big B is going to be B implies A, right? I mean,
yeah.
in mathematics, we have to pick a letter. If we're trying to write a definition, we have to just pick some variables and try to write a simple definition. Like we would never try to define the converse of this as the definition of converse. That would be insane. Like people would be so confused, right? We just use a letter for the hypothesis and a letter for the conclusion. It just so happens that P's and Q's are what we usually use to define. And now we're going to be using the P's and Q's so we can relabel the whole thing with a different letter. Like I'm sure you can, but I'm sure you both can write the converse of this, right? I'm sure you can both, you just put this here and you put this here. That's no big deal. But when we write the contrapositive, using A's and B's and arrows and knots, what is the contrapositive of if A, then B?
Not B, arrow, not A.
Exactly. So we know we're going to put a knot in front of that whole B and then we're going to have an arrow, and then we're going to have a not in front of now this whole A. So I don't mind that I had a bunch of parentheses because I'm putting a not in front of that whole thing anyway. And then we start hacking away. We start realizing, okay, I want to simplify this. I can use De Morgan's law and bring the not through here, right? If we use De Morgan's law and bring the not through the or, what does this expression, this hypothesis, this not be become? Because this is our not be, right?
It becomes not P and not Q.
And what is not Q?
Q.
Good. So that's our hypothesis now. Arrow. And now we're going to bring this not through this parentheses. So it's De Morgan's law because there's a big old fat or in here. So the first thing we're going to do is bring the not through and apply De Morgan's laws to negate these two components and flip the or to the.
So the or becomes an and it becomes not P implies not Q. Oh, the whole thing. Oh.
Because this whole thing is a component. This is like a not C or D. So we have a not C and a not D. You know, this is our D, this is our C. You know what I mean?
Oh.
And then not P implies Q. All right. Now we're going to keep going because we're going to practice the negation of an if-then is our last thing to do tonight. Because just to recall, let's just recall the rule for the negation. If we're going to negate an implication, we learned this last time, and it's one of the hardest things for students to learn. The negation of an if-then statement, you know, an arrow statement, is not another arrow statement. It's an and statement. Do you remember what the negation of?
Oh, not A and B?
Almost.
No,
It's
Oh.
A happened and B did not follow the way it was supposed to. So, oh yeah, so I'm going to add that to the things to remember. The other thing to remember is that the negation of P implies Q is P happened and the hypothesis Q failed to follow. I'm going to add that to our list of things. Like, you know, you don't have to remember everything, but there are a few things you really do need to remember. So we're gonna go ahead and bring the negation through this. What do we get?
Not P implies not Q. Oh no. P and not Q.
Nice. So it's P and not Q, and then we have this and now what happens here?
We're negating not P, but it's a negation, so it's P and not Q.
We're not negating the hypothesis. Did we negate A in the negation of A implies B? Nope.
No.
Keep the hypothesis exactly as it stands, no matter what it is. See what I mean? Whatever that hypothesis is, you keep it. Here, it's a not P. So we keep the hypothesis.
And not Q.
Nicely done. Now let's just see if we can do anything with this. There's a table of logical equivalences in section 2.1, and it talks about reducing things down. Let's see what this really says, just for kicks and giggles. It's a big old and statement, right? We don't have ors. All we have is and. So we don't actually need any parentheses at all if it's just a great big and statement. You agree?
Yes, parentheses only for ands and ors.
That's right. We don't, yeah. And maybe in other cases when we have arrows and stuff, but yeah, we certainly don't need any parentheses. So we can rearrange the order of these. This actually says that not P and Q, okay, I'm just keeping that the way it is because it's fine, implies. Now we can reorder this because and doesn't care where the components are. It's like the plus sign of logic, like 3 plus 5 plus 4 is equal to 5 plus 4 plus 3, right? Plus doesn't care. Neither does and. So we can group this together, and this says P and not P. Now we can put them together. And not Q and not Q. Do you agree?
Yeah.
Okay. Now let's think about doing a little grouping. It doesn't matter what order we do these operations, it's because they're all ands. So I'd like to challenge you to think about P anded with not P. Like if you made a truth table, P, not P, P anded with not P. Okay, let's just investigate.
That would be a contradiction.
Exactly. Because you can never have both P and not P because they always have opposite truth values. In fact, it is the canonical example of a contradiction, and we use the little letter C for contradiction.
Wow.
So it's always false. And now we're going to and a contradiction, which is always false, together with not Q anded with not Q. Well, what did we already learn about anding together something with itself?
It's true. It's a tautology?
It is just itself.
Oh, oh.
I mean, like having not Q anded with not Q isn't a tautology. Not Q will be false when Q is true.
Oh,
Not Q will be true when Q is false. So this will have two truth values. But when we AND it with itself, we don't get anything other than we would get if we just had itself. Remember? We did that with just a generic variable A ANDed with A. It's the same thing as A. Remember? Doesn't
yeah.
matter if that A happens to be not Q or something else. Anything ANDed with itself is just itself. But now let's think about it. A contradiction is always false, right? And we're ANDing it with not Q. But what happens when we AND together a false something with I don't even care what that is?
Oh, it's false.
Yeah, it's a contradiction. It will always be false. So this has a contrapositive that turns out to be this, that says if you have not P and Q, then you're going to get a contradiction. In other words, if this is true, then the conclusion is a contradiction and it's going to be a false conclusion. If this is false, you're still going to get a false conclusion, but in that case, the implication will be true, which defies intuition.
Wow.
Don't worry, I'm not going to give you a problem like that on a test, but I thought you might appreciate that sometimes something that's really really crazy nasty, right? When we first started, they can boil down and boil down to something quite simple.
Wow.
We're going to look at that idea of boiling things down to something more simple when we do our study about designing circuits, and we're going to start that next week, designing circuits. And it's closely connected with logical statement forms. So this is But really and truly, don't worry about pageables. This stuff is important though. This stuff you do need to know and work through those nice worksheets and come to office hours again.
Wow. Thank you, Professor.
Thanks for coming. I appreciate it.
Thank you. Have a good night.
Good
Have a good
night.